Hello, everyone. I'm going to be explaining the operating systems engineering throughout this channel. I'm going to be using the operating system concepts book, and it's actually the 10th edition, as you can see here. Okay, and those slides that I'm going to be using to explain the concepts are also, done by the authors of the book. All right. Yeah. So we're gonna start with chapter 1, and chapter 1 really gives a very shallow introduction about the operating systems in general. What is an operating system? Okay, if we would define operating system in one statement, I can say that the operating system is set of programs. Why? To control certain hardware. So we have programs, okay, and those programs control hardware. What does it mean? It means that the software you wrote to control something like of a microcontroller or something, you can call it as operating system because it controls hardware. And in a very abstract concept, you can see that, the programs, the logic that controls anything, it could be called an operating system. Okay. In vehicles, the modern vehicles, you have an operating system because vehicles are processed now by a microprocessor. And the microprocessor has certain logic, certain operating system that controls the process and it reads the sensors, takes decisions, and so on and so forth. Airplane, it has its own operating systems. Okay. Printer, washing machine, toaster, compilers, monitoring systems, whatever that you can think of as hardware that does certain tasks, those systems are being controlled by operating systems. Many of them have very special operating systems. Okay, so a washing machine has its own operating system. Is it Windows? Because Windows is an operating system. Is it Linux? Is it Unix? Is it Mac? Is it Solaris? Is it Android? Is it no? We don't know. Every washing machine has its own, and they are really very dedicated ones. Okay, as I mentioned before. Throughout your study in engineering, you have made your own operating systems by writing the code that would control a microcontroller to perform certain tasks on hardware. Move a robot forward or backward and, read the sensors, take decisions based on the readings of the sensor you read, and so on. This is what you did is an operating system. Okay. So what is an operating system? An operating system is a set of programs that control hardware. Okay. All right. So here it is. What is an operating system? A program that acts as an intermediate layer between a user and the computer. This user doesn't have to be a human. It doesn't have to be a person. It could be anything. It could be a person, it could be a robot, it could be another machine, it could be another program, a client that is making use of server services, whatever that is, okay? So the user can be anything. Operating system goals. So what are the goals of an operating system? Is to execute user programs and make solving user problems easier. What does it mean? I mean, the first one is very, very clear, right? Execute user programs. Fine. What is make solving user problems easier? Imagine that a user is writing a program, okay, to control a vehicle as an example or whatever. If there is no operating system that is installed on this vehicle, then the user needs to write each and every line to control that hardware. So the user is going to be writing the code for the sensors, for the actuators, for whatever that is needed. But if you have an operating system customized for this vehicle, then the programmer now or the user can literally call the services provided by operating systems, right? So you have an operating system here that is installed on this vehicle, and the operating system will provide services, and now this user can literally call the service instead of writing the service from scratch. That's number one. Number two, writing the service from scratch doesn't guarantee that the service will literally run properly, right? Because of the bugs and so on. But if we write the operating system once, make sure that every module, every service are working efficiently and correctly, okay, then now we can reuse this services provided by the operating system for many, many users to use those kind of services. Okay, so I hope this is clear. So make the computer system convenient to use, of course. Look, if the user is going to be writing all the code from scratch, it's not really convenient, right? Okay, but if you have an operating system that is already written and the operating system gets installed on the hardware, then those users can actually use the services provided by the operating system, which makes their lives easier and the use of the system much more convenient. And of course, because we're writing the operating system and we can make sure that this operating system is very efficient, as you will see throughout this course. Okay. All right. Now, what is the computer system architecture? You can see the computer system architecture as layers. So you have the hardware layer. What is the hardware layer? It's, the computing resources. This word is the basis of this course. Operating system engineering is all about resources and how you can utilize resources, okay, and how you can safely schedule resources, and so on and so forth. Those resources could be CPU, memory, I/O devices, anything that you have as a resource for the purpose of computations. Time Time is the most important resource that we have in operating systems, and we have a whole chapter dedicated to time, chapter 5, okay, that works with the scheduling and so on. It's all about time, right? So time is one of the most important resources that you're going to be dealing with in this course. All right, how about operating system? It controls and coordinates use of hardware among various application and users. You tell me, but that's easy. I mean, it's not really. Throughout this course, don't think about the hardware and the system in general as a single user. No, we're not going to be dealing with single user. You have many users are literally accessing the hardware in the exact same moment. Okay, so it's the problem is much harder than what you think. We have now application programs, just like any application program that you use, Word, Excel, PowerPoint, even any compiler that you use, those are the application programs that you use. So if you look at here, you will find that we have hardware. Above the hardware, you have operating system. Okay, you have here an application programs. Okay, and you have the user, the higher layer. Of course, as I mentioned, the user doesn't have to be a person. It could be a person, it could be another program, a client that is using the server, anything that you can think of. And the relationship between user and application is binary relation. So basically, it goes bi-directional. So the user asks the application to do something and the application responds to the user. Same with the application program. Here the application programs deal with the operating system as a client-server kind of thing. So the application programs literally ask the operating system for service, and the operating system responds back to the application programs. And here the operating system controls the hardware, and the hardware responds back to the command of the operating system. And you should not find a direct relation this way. So one of you should ask something like, okay, but you know what? When we started programming, we have used something like printf in C. And what printf does is it takes the whatever that you want to print and puts it directly on the monitor, right? So this means that we can literally communicate directly with the hardware. I say, no, wrong. That's wrong. That's not what's happening. This printf that you write literally talks to the operating system. It does not go directly to the monitor. No. It calls a service from the operating system. Okay? So it hands in whatever that needs to be printed to the operating system. And then the operating system takes it, and the operating system does its magic, which is not magic at all. You will see throughout the course that, how this is done. But for now, let's say it's magic. So the operating system will do its magic to get whatever you want to print into the screen. Okay? All right. Of course, as I mentioned, users can be people, machines, whatever that you can think of. So here is a better drawing than what I did in the previous slide. So here you have the user. Okay, the user have a bi-directional communication with the application program. Okay, the application programs communicate with the operating system, and the operating system communicates with the computer hardware, as you can see. Okay, the relation is bidirectional, so it's a call and a response. Okay, so the user calls the application programs, and the application programs respond. The application program calls the operating system, and the operating system responds. The operating system calls the computer hardware, and the computer hardware responds. Okay? So what operating systems do? So what do they do? Yeah, it depends on the view. Okay? So you have here the users. They literally require something. They seek something in operating systems. What do they seek? Well, ease of use. So you don't want an operating system that is really, really hard to use. And of course, as a user, you want good performance. Okay? The user doesn't really care about resource utilization. Okay? You need to get a system that is very easy to use and you get an amazing performance. How the system will be using the resources, you don't care, right? And think about it. When you bought a computer, you never thought about how the CPU, memory, hard disk will be utilized, right? All you care about is it easy or not, okay, as an operating system, and is it the good performance, does it provide good performance, or is it slow, does it have problems, and so on. Which is fair. I mean, if you go and buy a single computer, personal computer, yeah, you can easily find something like that. Now, shared computers. What are shared computers? Before I explain this, let's first see what are shared computers. A shared computer is a computer that has many users working on it. Okay, so imagine that you have a system like that. Here is the computer, and you have user 1, user 2, user 3, user n. They're all using the same computer. You might tell me, I've never seen something like that. Well, you know what? It's very common. You know, every one of them has its own terminal. So they have the monitor, they have the keyboard, okay, each and every one of them, okay, but all those are connected to one central big computer. What does it mean? It means that all of them are using the same CPU, right? The same memory, and probably the same storage. But they don't know about that. This user feels as if, you know, he's the only one using the computer, same as this user, okay? So we call those shared computers, okay? Examples, you know, mainframe, many computer, you know, those must keep all the users happy. How can those users be happy? Each and every one of them should feel that they are using the computer solely, so they don't really share it with anyone. All right? In order to achieve that, the operating system should work as a resource allocator. What does it mean? Well, the computer will decide that this user will have this amount of memory and this user will have this amount of memory. The CPU is going to be divided into cycles, of course. So this cycle is going to be given to one user, and the other cycle is going to be given to another user, and so on and so forth, as you will see in this semester. Okay? So they should work as resource allocators and program controllers. Okay, they will decide which program to be loaded into memory, which program will be taken out of memory, and so on. Okay. The objective is to make, efficient use of hardware. That's the main objective, by the way. Why? Because efficient use will make everybody happy. Imagine if the execution is not efficient. So the first one will be bothered a bit. The second one will be bothered much more because the second one is waiting for the first one, and so on. Okay? So in order to make everybody happy, the execution has to be efficient. Okay? And also managing the execution of user programs, as mentioned before. Users of dedicated systems, such as workstations, they have dedicated resources. Okay? But frequently use shared resources from server. Okay, so they do have the same problems of the shared computers. Okay, how about mobile devices? Okay, like smartphones, like tablets. Okay, we call them resource poor. Why are they called like that, resource poor? Because the amount of memory you have in a mobile is definitely much less than the memory you have in a computer. Okay, the storage in a mobile is much less than the storage in a computer, and so on and so forth. So we call them resource poor. Okay, and they are optimized for what? Usability and battery life, of course, right? Mobile user interfaces such as touch screens, voice recognition, and so on need to be supported, right? Some computers have little or no user interfaces, such as embedded systems. Okay, and they do exist in devices and automobiles and so on. So those kind of systems, like the operating system as example in a washing machine, okay, they don't have much interface, right? Maybe a button that will, start the execution, another way to choose the program and so on, but that's it. Okay, the system itself works without any interference from the user. Okay, so the user doesn't have any intervention. All right. So if we want to define the word operating system, literally you will not find a unique definition for it. Okay, and big concepts, it's very hard to find a unique, agreed upon definition for huge concepts, right? If you look at the artificial intelligence as an example, you will not find a unique definition for it. If you look at smart city as an example, you will not find the unique definition for it. Same with operating systems. Even though operating systems are much, much older, yet we don't have a unique one for what an operating system is. Okay, but we know that the operating system needs to do some stuff that we all agree upon, like basically allocate resources, efficient execution. In some systems, safety is very important, like, spacecrafts as an example, whatever that is. The efficient execution in TVs, because, if TVs and so on don't have efficient execution, image will flicker, as an example. Especially because it's a real-time system. You will know what a real-time system is later in this course. And it's funny that people use real-time for fast, which is a huge scientific mistake. It is not. That doesn't mean fast at all. Real-time is something else. Anyhow, so as I mentioned here, the operating system definition, it doesn't have universal accepted definition. It does not. Okay? Every thing a vendor ships when you order an operating system is a good approximation. Okay? Of course, it varies widely depending on what operating system you're getting. The one program running at all times on the computer, what we call it kernel or core. Kernel or core. So we have here, if you want to imagine what an operating system what it looks like, you have here kernel or core. Around it, you will have what we call system programs or programs. Then around it, you have application programs. That you can get with, okay? So the kernel of an operating system is the set of software that has to be working all the time. It has to be working all the time, okay? It cannot stop working. If it does, the system freezes. How about the system program around it? It's the set of programs provided by the operating system. Some operating systems consider something like, the TCP/IP for communication is part of the system programs. Others don't, by the way. Okay, but some of them consider it as system programs. So it comes with TCP/IP protocol, and so you can use it as a system program to communicate with, the outer world that is far from your computer. So those are system programs. And then some operating systems come with application programs. We all know about that. So a system program ships with the operating system, but not part of the kernel. Why is it not part of the kernel? Because it doesn't have to be working all the time. So memory management or memory manager is part of the kernel. You cannot have an operating system working without managing memory, right? Okay, but TCP/IP, it doesn't have to be working all the time. So memory manager is part of the kernel, but TCP/IP is a system program, okay? So a system program is, something that is being shipped with the operating system, but is not part of the kernel. How about the application program? All programs not associated with the operating system, like what? Any text editor that comes with the operating system, or you can install it or whatever. This is an application program. So today's OSs for general purpose and mobile computing also include middleware. Middleware. What is a middleware? A set of software frameworks that provide additional services to application developers, such as what? Databases, like multimedia, like graphics and so on. Okay, so as an example, the iOS users, you would get something like iMovie with the operating system, that helps you do whatever, multimedia you want and so on. Okay. Now, let's start with an overview of computer system architecture. Is this part of operating systems? No, it is not. Why are we doing this? As I mentioned, operating system is controlling hardware. And because it's controlling hardware, you need to remember what kind of hardware we are trying to control. Okay? So, here is a diagram. In an operating system, here you have the memory. The hardware, memory. And this memory is being shared by all components, like CPU uses memory, of course. Disk controllers, they do use memory. How? Well, if you want to read from the disk, they get the information you need from the disk and put it into memory. Why? In order for you to see it or use it. Okay, if you want to save data, you get it from the memory, and the disk controller will write it to the disk. And you have USB controllers, mouse, keyboard, printers are all connected through the USB controller. Okay, why does this use the memory as well? Well, when you write something on the keyboard, you need to see it in monitor. How? Well, the common space here is memory. So the keyboard here will get the information into the memory, and the monitor will get it out of the memory and so on. So this is how, you can see system organization, computer system organization, that one that we're going to be building an operating system for. So you can actually literally control each and every one of them. Okay, computer system operation. You have here I/O devices. Okay, and the CPU can execute concurrently. This is a very important word for us. Okay, all our work in this course is concurrent. What does it mean to be concurrent? Two tasks need to execute concurrently. So not in a sequence, but concurrently. Of course, that's what all the books say. I kind of have a different theory about it, and it's up to you to follow what I see or the book states. I see that even sequence is a special kind of concurrency, of course, and you will see it when we go through the course. Anyhow, each device controller is in charge of something, right? So as you can see here, the disk controller is in charge of the disk, all the operations that happen in the disk. The USB controller is in charge of the whatever that connects using a USB, like the mouse, the keyboard, the printer, and so on. Okay. And each device controller has a local buffer. Of course, you have a buffer here. So when you want to write into the disk, you literally, here, you write into the buffer. The disk controller takes from the buffer, put it in the disk, and so on. Okay. The CPU moves data to main memory, from local buffers. Okay, I/O is from the device to local buffer of controllers. Device controllers inform CPU that it has finished its operation by causing, what is this word? Interrupt. So in this slide, we see the word concurrent. Okay. We see the word device driver, which is not really important. You just need to know that this is the program that controls the device, the software that works as a controller. And we see the word interrupt, very important. Common functions of interrupts. What do we do with interrupts? What do they do? Why are they very important? The interrupt, look at this, transfers what? Control. It transfers control to the interrupt service routine. What is interrupt service routine? You can see it as software that handles interrupt. We can also call it interrupt handler. Okay, interrupt handler. Through the interrupt vector, which contains the addresses of all service routines. So, you have here interrupt. The interrupt goes to the, I'll call it interrupt handler. This interrupt handler deals with interrupt vector. This vector has addresses. It's an array of addresses. This address points to, it's a pointer, right? What does it point to? The code of the first service. It could be, let's call it display a character. So all it does is takes a character and put it into the monitor, okay? As an example, here, another service, which is write to disk, as an example. Another service, read from disk. Do you see? That's why I told you when you use printf, you don't literally write into the monitor. No. You call the interrupt, okay, that transfers whatever you want to write into the display. Do you see? Here it is. All right. What is this very important word? Trap. Trap, also called an exception, is a software-generated interrupt caused either by an error or a user request. Those who studied something like any high-level language, Java as an example, also Python, you do know that you have exceptions. You can try and catch an exception. You can also generate an exception. Okay, so you can request an exception to happen or to occur. Or if there is an error that happens, you can catch the exception resulting from this error. Any operating system is interrupt driven. Interrupt driven. Also, we call it event driven. Okay. Other operating systems, by the way, are time driven, okay? And I'll talk about it later, but they're very, very special cases. We call it polling, okay? They're based on polls. We'll talk about them later. So, if they are interrupts, that's how it works. The operating system here, the user program is working. Here is a user program, okay. Here it is. You have here, this is an idle case. Okay, and so this is idle, the iOS is idle. Okay, and then here an interrupt happens, IO request. So the data gets transferred from IO. When the transfer is done, here, you go back to idle, as you can see, and the user program here, it gets signaled by the interrupt, as you can see, and then it starts handling the interrupt again, and so on and so forth. So it's kind of coordination between here the I/O device and the CPU, as you can see. Who is executing the user program? The CPU, right? Okay, what is the I/O device doing? Handling the interrupts, as you can see as well. Okay, so it's kind of here coordination between the two of them, as we will see something called DMA in the next chapter. Okay, so how do we do interrupt handling? The operating system preserves the state of the CPU by storing the registers and the program counter. Why? This will be very obvious in chapter 3, but let me talk about it now. Imagine, you know that the execution of the program depends mainly on memory. So the memory contains the registers and so on, and the program counter. What does the program counter do? If you have here code like that, let's assume this is the program. Here are the lines. So the PC, the program counter, points at the statement to be executed. And the result of previous executions are memory pattern and registers, right? So if you want to stop executing the program to handle the I/O that is happening, you have to save where the program counter is and where the memory contents, so what the memory contents are. Why? If you don't do that, and then you handle the I/O, and then come back to the program, you will have to execute it from the beginning, which is very wrong, and it's not efficient, right? So what is the solution here? You save where the PC is, and when you, the program counter, and when you were in this program counter, what were the registers? Okay, so the contents of the registers and the memory. So when you come back, you put everything as it used to be. So as if you never left. And then you continue from where you are. Okay? Okay. So here is the interrupt drive I/O cycle. Here is the CPU. You have device drive initiates an I/O. So here is the I/O initiation. So here's number 1, then number 2, then you go number 3. The initiated I/O, see here, you have the input is ready, the output completes. You know, if there's any error that happens, you go back to the CPU receiving interrupt. So the I/O informs CPU that, you know, I/O is done. Okay? And then you continue here, you know, the interrupt handler, okay, process data that you have received from the interrupt, and then, the CPU resumes processing and goes back and so on and so forth. Here is the cycle of it. This cycle will be very clear in chapter 3, because in chapter 3 we're going to be handling the process life cycle. And of course, the process life cycle, if the process has an I/O, then it has to go through this process again, okay? All right, and we're going to be talking about the I/O structure in the following session. Thank you.